Hello everyone, my name is Lulin Zhang. I am a PhD student under the supervision of Ewelina, Rupnik, and Marc Pierrot-Deseilligny. Today I'll present our work Feature Matching for Multi-epoch Historical Aerial Images. The goal of our research is image alignment. Given a set of images, our goal is to find the similar points, or we can call them feature correspondences, and use them to compute the positions and orientations of the images. Here, I displayed an example of two images taken at the same time. As you can see, the lower part of the left image is overlapped with the upper part of the right image. In the field of feature matching, the methods can be divided into two categories, handcrafted and learned methods. According to the Image Matching Challenge in 2020, SIFT and superglue take the lead. We apply SIFT and superglue on the image pair displayed before, and here are the results. The blue line connecting 2 points of the left and the right images represent the feature correspondences. As we can see, both methods recovered a lot of good correspondences. What will happen if we are facing images taken at different times? Here I displayed two images of the same scene taken with a time gap of 16 years. As you can see, the scene changed significantly. A lot of new buildings arose. The color tones are very different. Obviously, it is very challenging for multi-epoch historical image alignment, not only because the images look very different, but also because historical images are often accompanied with low radiometry quality and the deformation caused by scanning. We will apply SIFT and superglue on this image pair to see what will happen. This is the result of SIFT. We got 0 correspondences. This is the result of superglue. The result seems not bad. However, when we look at the details, we can see the precision of the location is poor. This is not acceptable for high-precision ground surveys. This is the result of our method, which is capable of recovering a large number of precise correspondences. Certain previous works are devoted to align multi-epoch. There is a manual method, which is to process different epochs separately and use manually measured GCPs for multi-epoch co-registration. The shortcoming is that manual GCP measurements are laborious or even impossible. There are also automatic methods that process multi-epochs together using the inter-epoch correspondences. For example, use flight plan as guidance to match multi-epoch images. The shortcoming is that a flight plan is not always available. Or use SIFT to match multi-epoch images. The shortcoming is that SIFT is not sufficiently invariant over time. It is only suitable for simple cases with limited scene changes. Different from the previous works, our method exploits 3D geometry to narrow down the search space. It is fully automatic, it does not rely on auxiliary data, and it is robust against drastic scene changes. The key idea of our method is to use 3D geometry to improve matching performance. This idea comes from the observation that RGB images have the following shortcomings. Their appearances change over time. They also change with varying view angles on non-Lambertian surfaces. Besides, self-similarities such as repetitive patterns favor false matches. Fortunately, 3D geometry such as DSM makes up for these shortcomings perfectly. Here is an example of a pair of images taken from the same spot at different times. As can be seen, they look very different because the scene changed a lot. However, the corresponding DSMs look very similar, which is reasonable as the 3D landscape is more stable over time. Here is another example. They are images of the same vegetation. They look different due to non-Lambertian reflection. They also present self-similarity, which makes it difficult for matching. However, with the help of DSM, it becomes much easier to tell the correspondences. That is why we designed a rough to precise matching pipeline to take advantage of DSMs for multi-epoch image alignment by matching DSM for rough registration and reducing ambiguity in precise matching. Here is the pipeline of our method. It consists of 3 parts of processing. intra-epoch, inter-epoch, and combined. In the intra-epoch part, we process each epoch individually via a SFM pipeline to get the image orientations and the DSMs. Now the inter-epoch part, which is the most important part of our pipeline. It is a rough to precise matching strategy. Based on the image orientations and the DSMs from each epoch, we perform rough concentration by matching the DSMs. Then, use it to guide precise matching. We perform patch or guided matching to get tentative correspondences, followed by removing outliers with 3D ramsec and local context validation. In the combined processing, we use our correspondences to get the refined orientations in a bundle adjustment routine. Firstly, I'll explain the details about the rough concentration part, then the precise matching part. The goal of rough concentration is to get correspondences in two DSMs so that we can put different epochs into the same coordinate frame. Here I displayed the two DSMs from different epochs. The red rectangles indicate the overlapping area. When we applied superglue on them, we got no good correspondences. It is reasonable as the superglue is trimmed on small images in order to perform in real time, so it got inferior results on large images. Besides, superglue is not invariant to rotations larger than 45 degrees. Therefore, we introduce a tiling scheme and the rotation hypothesis to improve the performance. And we got this, a large number of precise correspondences. Here are the details for the tiling scheme. We divide both DSMs into M and N tiles, followed by matching M multiply M tile pairs individually. Then, we match the correspondences and apply ramsec to remove outliers. As for the rotation hypothesis, we rotated the secondary DSM by 90 degrees 4 times to get 4 sets of correspondences and keep the one with the largest number of inliers. We also considered using orthophotos for rough concentration, but experiment demonstrated that fewer correspondences were recovered because the radiometry changes are more obvious than 3D landscape. In conclusion, we have 3 contributions in the rough concentration part. The first one is to match DSMs instead of original RGB images, because it has the following advantages. It removes the redundancy caused by the forward and side overlapping areas. It enables a follow-up search for global inliers. It decreases the combinatorial complexity caused by rotation ambiguity. It guarantees stable information over time. The second contribution is the tiling scheme to upscale the learning-based feature matching algorithms to high-resolution images. The third contribution is adopting the rotation hypothesis to handle rotation larger than 45 degrees. Now let's move on to the precise matching part. We hesitated between DSMs and RGB images for precise matching, so we did a test for comparison. As you can see, we got more correspondences on DSMs because they are more stable over time, but they are too noisy to provide accurate results. So we choose to match RGB images by narrowing down the search space based on co-registered DSM, which will give us correspondences that are both accurate and robust. There are 2 options in our pipeline to do precise matching. The first one is guided match for handcrafted methods like SIFT. We project key points of one epoch to the co-registered DSM and back-project them to another epoch for prediction. And we only search the neighborhood of the predicted location to reduce ambiguity. We also use the co-registered DSM to calculate the scale ratio and the rotation between the image pair, and use them to check the scale ratio and the rotation calculated by SIFT. For example, the scale ratio of this image pair is around 2. The rotation is 180 degrees. This is our fourth contribution, which is to narrow down the search space with the guidance of the co-registered DSMs. Another option of precise matching is patch match for deep learning methods like superglue. We also resort to co-registered DSM for prediction. This time is to predict the corresponding patches that are free from scale differences and the rotation, and feed them into superglue. Now we will have a look at the experiment on a dataset with drastic seam changes. As can be seen, the seam changed significantly between two epochs. We apply our method on them to get the inter-epoch correspondences and use them to refine the image orientations in a bundle adjustment routine. Here is how we evaluate our method. We calculate the DSMs in each epoch, then do a subtraction to get the difference of DSM, or we can call it DOD. Ideally, the DOD should only display the seam changes, but in real case, a dome effect would appear like this due to poorly estimated camera parameters. Here I displayed two sets of DODs. They are derived from orientations based on 3D Helmert transformation using GCPs. For the first one, we use 3 manually measured GCPs, and for the second one, we use the GCPs automatically recovered from our rough registration step. We can see the dome effect in the two DODs. The third and the fourth DODs are derived from orientations refined in a bundle adjustment routine with our correspondences. The dome effect is effectively mitigated thanks to our numerous and precise correspondences. In the meantime, the real seam changes are reserved. A subregion of seam evolution is displayed below. A seaport as well as several new buildings emerged and are well detected with our method. We also applied our method on a dataset that witnessed an earthquake in order to see if the result is precise enough for detecting earthquake displacement. We have two epochs in this dataset, one before and one after the earthquake. Here we displayed the ground displacements caused by the earthquake. The first column is the ground truth displacement provided by the Japan Meteorological Agency. The second and the third ones are from orientations based on 3D Helmert transformations using GCPs. The fourth and the fifth ones are derived from orientations refined in bundle adjustment with our correspondences. As can be seen, an uplateral strike-slip movement along the sea is present in the fourth and the fifth columns, which is coherent with the ground truth. But we can't see the same signal in the second and the third columns. It means that the refined orientations are precise enough to detect earthquake displacement thanks to our inter-epoch correspondences. Thank you very much for your attention.